So we've generally been talking about dynamics thus far, and we've sort of been using this idea that the sum of forces on the system tells you what the time rate of change of linear momentum is, and the sum of torques on the system tells you what the time rate of change of angular momentum is. And this, using these equations basically boils down to asking the question, what are the dynamics of the system? That is, how does the system evolve in time? Well, one sort of simple limiting case of that is actually the static case, and it's worth looking at the static case a little bit just to sort of illustrate some of the ideas that are important and that also turn out to be important in the dynamic case. So the static case is the case where there are no dynamics. That is, the system is stationary. Okay? And if the system is stationary, what that actually means is that from a sort of time derivatives perspective, dl by dt is 0, right? The angular momentum of the system is not changing, and the linear momentum of the system is not changing, and they're not changing because nothing is moving, right? It's static. So you actually end up with sum of forces being 0 and sum of torques being 0, which is the static condition. So under the static condition, it must be the case that all the forces acting on the system added together add up to 0, and all of the torques acting on the system added together add up to 0. So I'll just do one sort of simple example of that to illustrate the idea that in order to figure out what's going on in the stationary case, you actually need to use both of these conditions. And it's kind of a standard textbooky example. So we've got a sort of bar that's attached to the wall with at a pivot point, and maybe up here at some distance there's a rope that comes down and is attached to the bar. And then hanging off of the bar we have some mass, big M. Okay? So this might be something you would be using to suspend something. It's like the design form you might use for a crane, right? And if you were designing that crane, you'd probably want to know things like, well, gee, how strong does this cable have to be? Like, what's the tension in this cable? And boy, I kind of would like to know what are the forces that are being exerted on the pins here, because like if this pin is, a certain diameter of steel, it can only withhold certain shear forces before it fails. So what are the forces on the pin? Right? And those are questions that you realistically would like to answer before you, say, hung someone in this in an elevator off of this, or whatever you are doing in building this thing. So, and we can use this sort of idea of the stationary case or the static case to try to identify what those are. So we're going to take the same approach that we have been for figuring out dynamics here, but instead just require that the sum of forces be 0 and the sum of torques be 0. And when we think about that, we really need to identify what's the system that we're going to deal with and what are the parts of the subsystem. Well, pretty clearly one system we could deal with is this mass. That's not super interesting from a free body diagram perspective, but we might as well draw it. So there's, I'll call this T2 is the tension in that mass experiences a force due to gravity, and it also experiences a tension pulling up. That's T2. So pretty clearly from looking at that subsystem, you can say, okay, the tension in this cable is just the size of the gravitational force, right? A somewhat more interesting system to look at is this member that's holding out this bar, the sort of crane's arm that is holding up the mass, that has this cable attached to it and also has the pin attached to it. So let's look at a free body diagram for that. So if I cut that out of the rest of the universe, I have T2 acting down on it at the end, right? I have whatever the cable tension is that's acting at this location. And finally at the pin actually can exert a force up. I mean, you could imagine sort of pulling down on this thing and the pin actually resisting up. You can imagine pushing up and the pin resisting by pushing down. You can imagine pushing in and the pin resisting by pushing back out. This pin actually can exert a force in any direction that it wants to. And that's because it is a constraint force. It's whatever force is required to keep this pin fixed here. So there's some pin here force, and I'll just say it's in this direction, because it kind of seems to me like it might be, but it's in an arbitrary direction. Okay, so if I look at that free body diagram, I can see I've got quite a few unknowns, right? I don't know what the tension in the cable is. I don't know what the X component of that pin force is, nor do I know what the Y component of the pin force is, right? So I actually have 3 unknowns here that I'm trying to identify. This is really the only body in the system, right? There aren't any other objects that it makes sense to sort of cut out of the rest of the universe. I mean, I could sort of cut out this support, but then I'd end up in not actually learning very much by doing that, because I'd say, okay, the pin force has to be equal to the support force, so it wouldn't be terribly interesting. The cable, I'm going to imagine, is massless, so that's not a system that I can talk about. So really, it's just this system. So I've got 3 unknowns. Well, how am I going to figure out what those unknowns are? Fortunately, I also have 3 equations, right? One equation is that the sum of torques on the system has to be 0, right? One equation is that the sum of forces in the x direction has to be 0. And one equation is that the sum of forces in the y direction has to be 0. So I have 3 unknowns and 3 equations. In principle, I ought to be able to figure that out. You can, for example, pretty clearly say right away, if I look at this, if I say sum of forces in the x direction, well, that's going to be minus the x component of the force plus the x component of the pin force. Sorry, the x component of the tension minus the x component of the pin force. Excuse me. By the same token, if I were to sum the forces in the y direction, right, that would give me the positive y component of the tension minus mg, which is the value of T2. So it's pretty easy for me to figure out what the y component of the tension is. And finally, if I were to say take a sum of torques, right, well, a sum of torques, probably the easiest point to calculate the sum of torques about would be the pin. In this case, that would give me whatever this distance is. So let's call it L sub c for the cable distance, and this is L, right? So the sum of torques would be plus L sub c times the y component of the tension minus L times mg, which would be so the y component of the tension gives me a counterclockwise desire to rotate. The mass, the mg, the force due to the mass pulling down, gives me wants to rotate the system clockwise. So that's why this torque is a negative torque, and I'm assuming in the k-hat direction, this torque is a positive torque in the k-hat direction. Finally, note that I've talked about tx and ty, but I am assuming that I know what this angle is here. If I know what this angle is, then clearly, tx would simply be, if I call this theta, tx would simply be t times cos of theta, and ty is t times sine of theta. So at this point, I would be able to say, okay, that's 0, that's 0, that's 0. 3 equations, 3 unknowns. I should be able to solve this by simply applying the powers of linear algebra, which I'm sure you're confident with now.